Okay, so let's look at a combination of functions here and just a range of different little functional applications, I guess you could say. First of those is what we call a hybrid function, which we've spoken about in the past. Hybrid functions are really just in this case, three distinct functions defined over a specific domain. So that's what we're really focusing on here, is the domain that each of these functions are defined over. So in terms of graphing it, we just sketch the graph as normal. So we've got the first function there in green, x squared plus 5. So we'll call that 5. X squared plus 5, if we sketch the whole graph, looks like that. Okay, and that's the point 0, 5. But clearly this graph is only defined where x is greater than or equal to 0, which means I'm going to get rid of this section of the graph, and even more, or as importantly, make sure I've got a hollow dot there because it's not defined at x equal to 0. So the next part of my graph, the one in there in blue, is the graph of 5 minus x. So y equals 5 minus x has a y-intercept at 5. And if I put y equal to 0, I have an x-intercept at 5 also. And so it would look typically, let's undo that. Typically it would look like that. Gradient of -1 and going through there. But again, we need to stop and have a look. Well, where is it defined for? It's only defined for x equal to 0. So, get that one. So it's not defined for x is greater than 0, and it's no longer defined after -3. So -1, -2, -3 stops about there. Yeah. So let's check, and they're both solid dots. So as it turns out, the graphs join up at 5. And at x equal to -3, we get the point -3. 5 minus -3 is 8. So I get the point -3, 8. The final graph in yellow is just the line of y equals 8. And the line of y equal to 8 is just a straight horizontal line that goes like that. But again, we're only sketching it over the domain that's relevant, and the domain that we're interested in is where x is strictly less than -3. So let's just rub out the section. And so then there's our graph. Now, as it turns out in this instance, our graph is what we would consider to be continuous because they join up at each of the key points. So that both graphs join up there and they both join up there. So our graph is continuous everywhere. So that's a key feature. So what we should also consider, if I then needed to just work out some function values, so I wanted to work out f of 1 and f of -2. Okay, so to work that out, x equal to 1 only applies to this function here in green. So f of 1 is equal to 1 squared plus 5, which is equal to 6. So if I go to the point x equal to 1, well, had I done my graph properly, it would have increased sufficiently enough so that it would go through the point 16. All right, so maybe let's tidy that up. So this hyperbola, the hyperbola quadratic, actually increases a bit more steeply, okay, and goes through the point 16. All right, as opposed to f of -2, which domain does -2 fit into? Well, it's fitting into the second function. So f of -2 is equal to 5 minus -2, which is equal to 7. So if we go to -2, which is about here, it should be at about point there, -7, which it is. So it's not like you get 3 different values. Okay, there's my function by definition. And for each x value, there is only one unique y value. okay, for a function. So that's our hybrid graph. All right. Consider other things that we can, a few definitions, a definition of what odd and even functions are. Okay, and so they've just got a couple of definitions, yeah. An odd function, if I substitute negative x into the function, I just end up with the negative of the function. So in other words, if we look at this one here, f of negative x is equal to negative x cubed minus x, which is equal to negative x cubed plus x. If I take a negative out the front, I get x cubed minus x, which is the negative of the original function back. So that makes it an odd function. An even function, if you put negative x into the graph, you end up with the original function back. So f of negative x in this instance is negative x to the 4 minus negative x squared. So we're going to go here, which is equal to x to the 4 plus, well, minus actually, isn't it? So it's minus, undo that, minus negative x squared is positive x squared. And if we check that, that's the original function back again. All right. As opposed to x to the 4 minus x cubed, if I put f of negative x into there, I end up with negative x to the 4 minus negative x cubed, which is x to the 4 plus x cubed, which is neither. It's neither the original function nor it is the negative of the original function. So, you know, graphs can be odd, they can be even, functions can be odd or can be even, but they may not be either. So if we want to have a quick look in here and just check these ones. So let's go with f of minus x is equal to negative x to the 4 minus 2 times negative x, which is positive x to the 4 plus 2x. So it's clearly not the same as that one. And if I take a negative sign out the front, I end up with negative x to the 4 minus 2x, which is still not the same. So it's neither. Let's come into B. F of negative x is equal to negative x to the 4 minus 3 times negative x squared, which is x to the 4 minus 3 times x squared, which is the original. So that's an even function. Nice one. And you can see each of those individual components are odd themselves. So if we add them, which is the negative of x cubed minus 2x, which is the original. So therefore, it's an odd function. Yeah, so it's just a little set of definitions really that are sometimes useful to know. If we add functions together, we add functions together all the time. You know, x squared plus 2x plus 1, you could argue, is the addition of 3 separate functions. So if we add or multiply functions, a couple of things we need to be aware of. Well, there's our sum and difference, which makes common sense. Add them, subtract them, multiply them. All right. The domain, though, for each. So just think we've got 2 separate functions here. So our domain for the sum, the difference, or the product is the domain that satisfies both equations. So if I've got a root x times, I don't know, sine x or something like that, well, the domain of that is R. The domain of that is R plus union 0. So I can only have R plus union 0 if I'm going to use both functions. Okay. So in terms of working them out, they're relatively straightforward. F plus G is simply just root x minus 1 plus root 3 minus x. Okay. Let's talk about a common domain. Let's talk about the domain for all of these. So the first graph is x is greater than or equal to 1. The second function is x is less than or equal to 3. So they've got to be bigger than 1 and less than 3. So the domain for all of these graphs in here, the domain is going to be equal to, well, there's going to be 1, I'll just put it that way, 1 to 3. Yeah? Because if the numbers are outside those two values, one of those two functions won't exist. F plus g of 3, we just substituted in, which is the square root of 3 minus 1 plus the square root of 3 minus 3, which is equal to 3 minus 1, which is 2, which is root 2. Fg is the product, square root of x minus 1 times the square root of 3 minus x, which is, if you like, to simplify a fraction, x minus 1 times 3 minus x, using our index laws. Evaluate that at 2. We just get the square root of 2 minus 1 times 3 minus 2, which is 1 times 1, which is 1. That's just equal to 1. All right. But the key thing to remember is that domain part of it. All right. The range is just going to be determined by the values of the function in that particular domain. There's no rule as such. All right. What have we got here for this little example? If g of x is equal to x squared, show that g of u plus v plus g of u minus v equals. All right. So I've said in the past, a lot of the questions start introducing a lot of little variables and things like that, parameters maybe. So let's have a look. So g of x squared is equal to, so u plus v, g of u plus v is equal to u plus v squared, which is equal to u squared plus 2uv plus v squared. G of u minus v equals u minus v squared, which is u squared minus 2uv plus v squared. What happens if we add them? If we add them, we get 2u squared plus 2v squared, which is equal to 2 times u squared plus v squared. And u squared is simply equal to 2 times g of u plus g of v, which is what we had to show. All right. Last little thing we want to have a look at is addition of ordinates. And what our addition of ordinates is, it's a process by which we can sometimes sketch graphs that we may not know what they look like together, but individually we do know. So for example, I might want you to sketch the graph of y equals x plus 1 on x. Yeah. Now individually, I know what x plus 1 is. So if I just do a quick sketch out here, x plus 1 in green, I'll make it yellow, looks like that. The graph of 1 on x looks like that. And so the addition of ordinates says, okay, if I add those y values together, I can then get the graph of x plus 1 on x. Okay. Obviously, I can do the same thing for a difference. I can subtract the values or just sketch the negative of one of the graphs and then add the points together. So it takes a little bit of practice. And we've got a worksheet that we can have a look at here to help us. All right, let's try. So I think the biggest thing we should do is try and do our graph as accurate as possible. So y equals x plus 1. So we'll do that in a nice blue. So there's my y equals x plus 1. Okay. We've got a vertical asymptote for y equals 1 on x. And we've also got a horizontal asymptote. So let's do, there's my vertical asymptote. do a horizontal asymptote. And maybe in green, we'll do 1 on X. So 1 on X we know goes through the point 1, 1. So let's make that the point 1, 1 there. So our graph goes up like that, and then comes down that way, and it goes through the point 1, negative 1. So you might go through like that and up that way. Yeah. So now let's grab a different color pen and we add the ordinates. By add the ordinates means we go to each X value. So we'll do that. So let's plot a few points. So at X equal to 0, we have an asymptote, so we don't have to worry about that. So at X equal to 1, 1 on X is equal to 1 on 1 plus X plus 1, which is equal to 2. So I get the point 1, 3. So that's the point 1, 1. That's the point 1, 2. So if I add those 2 points together, I add the Y values together, and I'll get the point 1, 3. Yeah. If I go to the point X equal to 2, I get a half plus 3. So at X equal to 2, I've got that point there, which is at the point 2, a half. The corresponding point up there, which would be at the point 2, 3. And so I get a point up higher again. So if I bring this down, so maybe it's up there somewhere. So it's sort of, what happened there? So my graph is sort of coming out. So what's happening? I've got this blue line here, which at X equal to say 10, I get 10 plus 1, which is 11. That's the blue line, plus a little bit more, 1 on 10. At X equal to 20, I get 20 plus 1, which is 21, plus 1 on 20. So it's really the blue line value plus a little bit more. So really, this line here, if I extend my blue line further, this section of the graph is just going to get closer and closer and closer to the blue line. It'll never touch it because it's the blue line plus a little bit of the green line. What about in here? They're both at the same point there. So if I add those 2 points together, so what are those values? So maybe it's, no, we could work out a point of intersection. It doesn't matter. So it's 1.5 maybe. So maybe that Y value times 2 is about, I don't know, there. So maybe if we tidy up our graph a fraction, tidy it up a fraction, we're sort of there, approaching that line. What's happening in here? What happens as X is less than 1, say? So if we say put X equal to a half, I get 1 over a half, which is 2. I'll get 1 on a half, which is 2, plus a half plus 1, which is 3 on 2, which is equal to 3.5, isn't it? If I put X equal to, say, 1/10, I get 1 over 1/10, which is 10, plus 1 and 1/10. If X is, say, 1 on 100, I get 1 over 100, which is 100, plus, that's 1 plus a 100, 101 on 100. So it's really, it's that big green line value plus a little bit from the blue line. So again, if my hyperbola was to continue, my graph would approach it, but never quite touch it. Yeah, because my graph, my green line approaches x equal to 0 and never touches it, the same as my black line. The same as my black line. Let's think about what's happening below the axis, to the left of the axis. So let's think about in here. So the blue line is 0 there, plus the green line value of -1. So it goes through that point. Yeah. If I add these two negative values together, so it's what, -2 1/3 plus -1/3 nearly, or 2/3 probably. So it's down here somewhere perhaps. What's going, as I go out here, I've got this line here, this blue line, which is getting steadily bigger and bigger and bigger as a negative value, plus this green line, which is getting closer and closer to 0. So it's going to behave very similarly. Whoop. So we're going to go, well, let's think of a couple of things here we should think about. Is it necessarily a turning point there? No. All I know is it goes through that point. Well, let's think about our graph here. We've got these positive values and a negative value, haven't we? So if we keep working through, so I've got a funny feeling. So we've got this negative value in green plus a little bit of a positive. So it's just going to be a little bit above that line. So it must come up a little bit. How it comes up, it's really hard to tell. So, but we know the graph, just trying to make it a bit smoother, we know it's going to come back down and approach that asymptote. So it's a little bit messy just there. I'll just tidy that up a little bit. Can we be precise? No, we can't. Okay, there's only a few things that we definitely know. So if I was to grab my red pen, the only thing I definitely know is that point there is 0, that point there is -1. It definitely goes through there. The lines cross there, so that point there is definitely 2 times whatever that y value is. The lines cross there, and this point here is definitely 2 times whatever the y value is. Yeah. So all we really know is we've got a basic idea of what the shape is. All right. So it's called addition of ordinates. It's where we add the y values together, and it's not a bad idea just to get on Desmos or one of those sort of things. Just put y equals x plus 1 on x. That's a good one to practice with. Okay, sketch y equals x, sketch y equals 1 on x, and have a bit of a play around to see what you think the ordinates would be. But I'll give you a worksheet on this one.